Uh, Hi everyone. Welcome to this discussion. So I hope everyone have a great week. Today we are gonna discuss about the lecture of FVCOM based ecosystem models. So I will first show all the questions that I received before the class, and then Dr. Chen and I will answer them one by one. So. The first question is from Minwoo Park. Minwoo Park, would you please to say more about your question?
Okay. In a previous meeting, I asked about MPI issue that occur in 1D channel idealized experiment. At that time, the professor mentioned that instability can arise when a single node receives data from multiple domains. However, a real case model like the East China Sea model use a large number of processors due to computation time requirement. Uh, During grid division, problems arise due to complex constraints. Uh, One node often spans across multiple domains. In other words, MPI-related issues inevitably occur in real case. I'm curious if there are a method to eliminate or minimize these MPI issues when running real case simulation. And next, please. Uh,
Mhm.
okay. Also, FVCOM optimize and devise the grid using methods before running the model simulation. So I'm curious whether users can manually modify the divided grid. Or can users adjust how the grid is divided by inputting various options in Metis? This is my question. Thank you.
Mm. Okay. So later we can discuss the question, okay? So probably last time my answer to you is ex- not very exactly, okay? It doesn't mean you get data, so one point get data for different location, like three location get instability. They can cause the instability, but not always cause the instability. Like each trying to see more. Later we answer the question, okay? Okay, good.
So next one, Junyoung, would you please?
Yep, thank you. So my question is about the NIPM model.
Mhm.
So because the RSIM's biogeochemical variables are linked, like coupled with each other, so I think it's really important to set up a proper initial conditions. So
Yeah.
for the NIPM's case, I'm wondering how did the 3D initial conditions and also boundary conditions are generated and works. So
Okay.
I think it seems like we need to make it for all inorganic and organic state variables, but it would be really hard to find some observational data which can cover that
Yeah.
whole NICOPS domain. So yeah, that's my question.
Good. Yeah, good. That's a good question.
Uh, Next one, Ki-Hwan.
Oh yeah. Actually, my question is about the online and offline simulation of the FACOM jam. Actually, in the lecture they mentioned that the jam can run in both online and offline mode. And then
Mm,
I just wonder that, for example, in like a sub-mesoscale on frontal region, which have like a high frequency variability, so could the offline simulation can sometimes they can miss some key processes like
mhm,
due to the temporal decoupling from the physical model. So for example, if we save the model at
mhm,
our 1 hour interval, I
mhm,
think some kind of like high frequency variability they cannot really resolve in
mhm,
the FACOM gem model. So I
mhm,
just wonder that uh, how should we decide when the offline or online coupling
mhm,
became like necessary? And then I just also wonder that in the lecture they also mentioned the gem model, we can definitely use another forcing like a HiCom or any other forcing. So I just wonder when we have to use the online model to consider the
Yeah.
physical things.
That's a good question. Okay.
Okay, next one, Jimmy Seal.
Okay, my question is, African gem is utilized on unstructured grid, so that represents complex coastline. So I wonder that how does it reduce the numerical error in mass transports, such as advection and vertical horizontal diffusion, then structure grid is my first question. And second is phytoplankton are more likely carried by ocean current. So I wonder point is how does those they controlled to main vertical mixing and stratification in coastal water, and how does this physically control the timing of ecosystems blooms is my second question.
Okay, so these are all the questions I have received. Is there any other question?
Yeah, okay, let me read this question, okay. How does it the physical teleforcing affection stay variable equation? Certain optic maintain vertical mix and okay. Physical control time equals okay. Okay, good.
Yeah.
Okay.
Okay, so if there is no more questions, so we will start from the beginning.
Yeah.
Mm.
So if I answer not correctly, Dr. Lee can get more detail. My last time was said, if you had a one node receive the information with a, like you saw here, so with a, couple node, so then you probably can cause the numerical instability, cause some solution. But that's dependent on the case because I should see more clearly. Like East China Sea case, for example, you show this one, they probably not cause a problem. The reason because I was means is I means I means if you had one pawn, okay, you had one pawn, so you change the data between the two node, the one boundary in the node with two nodes we change it, a third node change it. However, this node also be used for others, okay? Because you get a CPU like cross this one here, so they be like this one here. So they'll be used here. They be used this one here, this line here. They used by they also used by this, but it's really depend on the case. Sometimes they can cause problems. Sometimes dependent. So it's hard to say. For example, you trying to see case like this way, you probably not cause a problem. Okay, because this node here, this node here, he get data, depending, you look over this one here, so then the automatic problem, but this one, because your domain too small, use too many nodes, okay? So too many can cause problem, but this one show the right side, 100, this probably not cause a problem because they had an interior region, they had a boundary region. But this one, sometimes you don't have an interior region anymore. You get too much node. Okay, so that's why dependent how how many node you can choose. My last answer said one node receive the data from different location, the three or four node, and one point they receive data from they can cause instability, but it's not always can cause the instability. But if you have interior region, so then you have a node cluster, there should be no problem. But the problem is now you get too many nodes, you get so close each other, so the data was changing for this node, also changing for another node. So then they call the problem. There's one data used for different kind of boundary. That's why you look at the right side here, you probably don't cause a problem. My answer to your question, the best thing is you test it. Okay, you use node, Okay, you use node, you can run the model. Once you run the model, if you increase node, you don't get a, you don't get a, you don't get a, you don't get a, like a speed up. That means you get too much node. Okay, you should, if you, like Jeff Cover did the analysis, if you choose node, certain node, the no speed was linear increase, no speed was linear increase. This means you choose right away. But when you certain, if you choose more than node, they get a flat. They not speed up anymore. In this time, you should not take it. You should stop. For example, you use 100, the 60 node, they can increase speed. While after 6 node, they flat. In this way, you don't want to choose more and more. Okay, choose more. That's cause a problem. So, but I don't have a like a one number show you what exactly how much node you should choose just by testing. But then in speed issue, I want to clarify this. It's not always happen. For your case, it's happen for small because your domain so small, you wish so much node. Okay, you wish so much node. Probably two node. You know, you had so much node. That's why the two node probably probably you use the same domain. Okay, but then 108 node for I look at the map for China C model. I don't think that can cause a problem. That should be okay. But I don't know how efficiency. I don't know, right? But I don't think cause problem. So that's why my answer to your question is I don't have a we don't have a one unique method criterion tell you how to change it by testing by yourself. Okay. Just testing to put your model wrong. Okay, choose so you want to see how many nodes you really need. So you can see, if you see the speed was a linear increase, choose no, that's okay. If you find the speed of something, like a slow down, so that's means you choose too much no. Dr. Lee, you want to add something?
Yes. So I want to say more about the metrics that you use in
Yeah.
FVCOM. So it is related to the second question. So for the metrics in FVCOM, we use it to divide the one domain into different partitions. And when metrics do the partition, actually there are two roles to do it. The first one would be metrics will try to make each subdomain in with a similar workload, which means that after do the partition, each area or each subdomain contains roughly the same number of the nodes or elements. So in that way, we run the model in a parallel way. So each CPU will have the similar workload and run in a similar speed. So this is row one. So for the second row, it Mattis want to mix each partition, each subdomain in a roughly round area. So it will, in this way, it will minimize the data transfer between different or neighboring subdomain. So in this way, it will you will get a better performance. So these are the only two roles for Mattis when it do the partition. So in that way, actually, you cannot directly ask Mattis to say, "Hey, for this domain, I'm really interested in it, and I want to put it in one partition." No, Mattis cannot do that. So this
No,
is
no,
my
one
answer.
thing is we did it before. Some people don't use the Mattis software. They was a decomposition by themselves, but output you know the file, the decomposition file use the message format. FECON can understand that, but no matter how you do yourself or the Mattis do automatically, so you have to be make sure that each domain you get the same each domain, each subdomain, you have to get a same node, roughly same node. I know, so we do a lot of ideal case before. So we use like a, in like a ideal case because domain is very small. So we should four nodes. So some people just use manually doing that. You can do the user input, but however, you have to get the exact format. Writing the format like things like a match request. Okay, but
So
I think
there
that's
is no
too complicated. Yeah, yeah.
so there's no option for user to 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 make to ask Mattis. There's no
No,
other
you had
options.
a no, you had a way to do that. When the FVCOM early development, when we do the, benchmark testing case, some people do that himself, just to make the decomposition. So then you can input, but you have to follow some format, make sure the exactly same format the match is fine. You can do that by yourself, but you don't have we don't have an option in the coding, set it you by your doing self, also do automatic. We don't have the option, but you can do that. Okay, you can do that. But we said we got a couple of people like we do the benchmark testing. No, the people in my group did this way. They did it the way they use like but this is a very simple case. For example, for each Tennessee case like so complicated. So other case, I think your resolution so not you have to count in the node. I don't think you can do. I don't think you want to do by yourself. The matrix can do for you, but we don't have an option inside. Like the user said, no, you can do by yourself or you can do automatically. We just kind of automatically done. But my answer is that you can do by yourself. Okay, you can do by yourself.
I
So
remember
they yeah,
in
but we
the
don't
in
have an
the
option for that. Sorry.
okay in the Dike module you kind of ask a certain region for specific processors. Is that true for Dike module?
Die module? No.
Dike.
Dike module. Dike module
Uh,
is a little bit different. No, Dike module, we only, we put a die there. So then, we had I think it's Dr. Chi, not a Gertie, okay? The Gertie do the single CPU, Dr. Chi put a parallel, but this parallel just, you can see, parallel just still do the decomposition. But I don't think a Dike module was considered in the maps. I don't think he did that. I don't think we have, but I can double check with Dr. Chi. Okay, but
uh,
you do the die module for some time, you can little bit slowly because the CPU waiting for the die for
yeah.
no we're waiting for die module. You have
Yeah.
to
So
wait
so
because you have to calculate two times. Like a die here, you calculate this time and another time, two times. But that probably was in the but however, when we do the max, I'm pretty sure we was trying to avoid, die module the line was in the was class two CPU. All right, I think we did something to try to avoid this can happen.
yeah,
Okay,
so for our current Dike module, we ask the user to provide the number of the dikes. So for
yeah,
example, in this case, there are totally two dikes. Then when we run the model, we ask the user to at least use three CPU. So the two dike will occupy, we will use two CPU separately. And
yeah,
for the rest of the domain, we'll use the last
yeah,
one. Yeah,
yeah,
so in that way, it will, just as Dr. Chen mentioned, it will avoid the data transfer across the DAC.
yeah,
But meanwhile, it makes the model runs really slow.
yeah. Yeah,
So
but
meaning that
if when we identify a special node for die, that model can perform is okay. Performance is fast. Okay.
meaning that user can specify certain number of nodes or region to specific CPU.
No, just for die, only for die. Not
Mm,
for special, not a user can say, okay, I want to use this domain here, I want a special CPU. No, only for die,
mm.
only for die, okay? So if you use a special CPU, so then you get into trouble. right? You specify the CPU, they're all computer waiting for you. You want to specify,
Yes.
I use 6 CPU, but another domain uses another CPU. So then the whole computation get, because, they have, each, when what how the domain exchange is, they have to run each one, process run. Run the one, they just waiting for neighborhood, right? So who finishes fast? They exchange the data first. If you only two domain, they just waiting for A and waiting for B, B waiting A. So after both ready, they exchange data. But you have ABC domain, ABC three domain. But if today, computer run the C fast, right? And the C fast and A fast, they change the data and the AC first, right? So then later on, for next time you put the model rerun again. Okay, probably B can be, but electronic issue, B can run fast. Okay, C is slow. They can A and B can change it first. That's the render. That's reason you get run a two cases. You probably don't get exactly the same result because this error can accumulated error. That's why the Jeff Cover, said that if we want to do that, so he put like a fix it. You can fix the CPU, let them know how they change the order. This way you can send result each time, but it's very slow. But then the function, I think it's after I heard it's after we update the coding, so this function has not been updated, sometimes not working, I heard, right? But nobody use that, that's the problem. If you want to use that, we can go back to look at this, so they see how the working, they ask Jeff Cover just update his software.
Dr. Chen, so last time Dr. Qi tried to test it's not working. But later Dr. Qi found that it is due to the O3 optimize 3 flag. So
Okay.
if you turn it off, it is working.
It's working. Okay, it's good. That's good to know. But you just said that you don't want to use the O3, no optimization, right?
Yes,
Yeah.
we need to turn off all the
All the
optimization.
all the operation off. That's what Jeff said too,
Yeah.
right? This way you can, they don't let the coding like a Fortran compiler to make the operation, right? They just let you control. This way you can get a equal result. Okay, good. Yeah. Okay.
So Miwu Park, did we answer your question?
Yes. Uh, is helpful for me. Thank you so much.
Yeah. Okay.
Mhm. So next one.
Oh, that's a really good question. To be honest, that's a really critical issue. Okay, so now when you do the model, we don't have the initial condition. So two things you can do that. One is just to get all the climatology data, all the many year climatology data, to use the data to build the initial condition. Just put the climate because you had a climatology like a gym, each monthly climatology, not one day. Okay, so you put there. Okay, then you run the model. So that's the one way we did it here. Another way you can do that. Some even you don't have a lot of climatology data. You don't have a lot of climatology data, right? So you assume this initial condition, the ecosystem variable only variable and vertically. Just you saw the vertically had a profile, right? For example, you change the deep regions are high, surface regions low. So then you saw that's every place is uniform, only vertical distribution. So then you run a model, they spin up. So then you think everything the horizontal spatial variability due to by physics. Right, the mixing to then later on you run for spin up, right? Spin up, certain time, so the model can really catch about, spatial distribution, everything, then you start running the model. Okay. Some people suggest like a people like a Earth and Ting suggest you have to spin the model for 1 year. You have to spin the model 1 year, right? Then tune the parameterization to make sure the local observation, then you continue on. Okay, so that's why, so most of the work I did before, I just use second way. I just use assume. You look at my paper, right? I assume, phytoplankton, like vertical profile of phytoplankton nutrient, the deep is high, shallow was, the top surface low, phytoplankton surface high, the decrease with depth, right? So then I use the N nutrient and the P, I can determine what the Z should be look like. Right? I use the MPZ structure. I can analytical solution. I use the observation profile, determine, then I run the model, see what happened. Come out pretty good result. But for domain like a northeast region, domain so big, sometimes because this region, if you domain small, you can do that. If region larger, like a Mid-Atlantic Bank, the Georgia Bank, and the Shelf region, so these structures very different, right? So that's why we use the climatology. Okay, but sometimes some region you don't have climatology, you have to use some assumption. Okay, that's very critical. That's very critical.
What is the variability in horizontal space, in XY space, as an initial condition?
No, when you do the second way, you don't have a horizontal spatial variability. You just assume everything uniform, horizontally. You only have a vertical profile. Then you run the model spin up, and then you have the mixing changes, you got a circulation changes, so horizontal variability, so variability can come. You got a river output, so horizontal variability then they build up. So you assume everything, everything on the horizontal and the horizontal variability, spatial variability caused by the, hydrodynamics. Okay, caused by the forcing. This way you can do that. But then if you use the climatology, you already had a horizontal variability. That's different, right? Horizontal variability. Because you climatology, you get a monster climatology, but you still be sure. You still need to run the model because the ecosystem had to equate to equilibrium state. If a system not an equilibrium state, that's why in my course, ecosystem modeling, I teach a student, I said, when you see the model is good now, you have to do the static analysis. You assume time dependent zero. Okay, so then you your model, you solve your model, put some condition. You want to show your model can reach to equilibrium state, right? So when you reach the equilibrium state, that means you have an ecosystem. If you run the model, just put a time dependent equal to zero, you run the model, you find that, for example, nutrient equal to zero, right? Like for example, there are also phytoplankton eat all the nutrients, for example, So the zooplankton, all the phytoplankton, they all just phytoplankton zero, and nutrient equal to zero. So your system is crap. So you don't have an equilibrium state. Is this way you're not able to run your model, okay? Right? So that's why you look at, I had a book, ecosystem book. I said the first time you had to do steady solution analysis. So you want to see your system you have the equilibrium state. So then you can see how the ecosystem has a perturbation happen, right? If perturbation happen, so your system can go back to equilibrium state. That means you're gonna, this system stable ecosystem, right? If your system cannot going back, go to another stages that we call it regime shifting, right? So that's sort of neutral stable. So they change your analysis. For example, you have a climate change. You got a warming, right? Warming system, the phytoplankton, everything changes, like a plume times changes. So then after this one, you reach another equilibrium state. For example, every year, for example, your plume was happen in the May. Because of warming, they make your plume happen in the February. Right? So this way you get a regime shifting. But no matter how regime shifting, you steady state without any forcing, you put in that kind, they should all the variables should reach to equilibrium state. If you're not in
Right.
equilibrium state, you're not able to run ecosystem model. Okay.
So
Well, answer your
to
question.
test
Yeah.
so to test that equilibrium non-time dependent state, we have to choose the constant boundary condition from the river, for example.
Yeah. For example, you want to test your model. Okay. You put an initial condition there. Okay. Just the initial every place condition. Then you run the model for. Most time we do. No, we just want to state. We put one value there. We calculate other value. For example, nutrient. Right? We put a nutrient contribution. We want to see the phytoplankton how they behave. And then you look at my older paper, 1969. So then you call the zooplankton that is equal to Libni state, right? So if they all just you get your whole equation. So you don't need to run a model more time. You just make the equation for everything time dependent zero, right? You see the equation, then you can see you give the condition that the system is balanced. Okay, so that's why then so that's called stability analysis, steady state analysis. After this one, you can determine. Then also you can run a model, right? You can run a model. No, you can, for example, you put the fresh water in, right? Put the fresh water in. So you put some certain nutrient. So then the that's not a steady state analysis. That's just simulation analysis. That's why now the issue come out. If you had a simple MPZ model, you can easy to do that, right? You just turn off the time dependent. So I can show you how to do that. So then you put a nutrient, for example, you could profile there. What the zooplankton should be look like. Okay, what the habitat you can determine by steady state. You can solve the equation numerically. Okay, you can get the equation. You can solve. Like a no equation. You can get this whole solution. Then you can see that this could something equal to zero now, right? Some parameterization. Be very careful. In my book, I use the example for MP model. Right? You can see if you choose a parameterization for some certain thing, you can get an infinity solution. Right? Be careful. That's why you can tune the parameterization, make sure system becomes an equilibrium state. But when a model like this model so complicated, it's very hard for you to do steady analysis. Right? So this way you just put a model some condition, initial condition, put a basic forcing so we do the 1D model test. Now most of the state analysis is the 1D model. Okay, that's the reason I want you to run the 1D model. 1D model is vertical profile. You put a heating, a wind on the surface. So you want to see that the system can go to steady state. Right? So that your nutrient get a cycle come out. That's a phytoplankton go to cycle come out. If you get a steady state to come out, that's mean your model okay. Then you run the 3D model. Don't go ahead and run the 3D model directly. You should do the 1D model to make sure your model has reached the steady state. No, not a steady state, equilibrium state. That's mean your system was balanced. Right? This way you can run the 3D model. Okay.
Yeah. Oh, thank you. And I have one more basic thing then, like TS data simulation in FVCOM. So does the RSM also can use data simulation for the biogeochemical variables? So if there are some observation data?
I don't suggest that. The reason because that's not like for example, we have a physical model. You do the data simulation, that's the math. That's the math. For example, you get a temperature, you do the data simulation because your model had a temperature for 10 degree, your observation 20 degree. You can do the simulation to judge your temperature. All right? This temperature is not alive. Right? However, some people do the data simulation for ecosystem model. I really against this way. Because, for example, you only can simulation for nutrients. Okay, because you got a bottom-up system, if you got bottom up system, everything, if a nutrient changes, phytoplankton changes, zooplankton changes, also detrital, everything changes, right?
Mhm.
So you can do data simulation for nutrient, that's bottom, because that's like a mass get in, right? So you change this one, the whole system change. But however, you cannot do the phytoplankton, right? Because this is the life cycle. The phytoplankton will take over the zooplankton. They're also by taken by zooplankton. Okay, they also and after his mortality can cause a detritus. It's all a life cycle, right? So this way you want to make sure you don't want to data simulation everything. You want to only do the one, like basic one, because the bottom up system, right? So you want to make sure you do the bottom one. But you just said my bottom one is nutrient input not correctly. I do the simulation. So then I see the whole system, how they change it. But you cannot choose like either one, like zooplankton, phytoplankton doing that. One guy was, in the south, you met, USA. I know the guy. I don't want to mention his name. He do everything. Okay, simulation. So that's why, that's really dangerous. So then you do everything. Nobody know what you. So you cannot determine the life cycle anymore, right? You cannot do like a flow chart or like ecosystem. The ecosystem is kind of life, okay, right? You want to see how much you're taking rate, what are they, how they determine that. But however, they do have some way to do simulation. They do have some way to do the data simulation, okay? What do they do? Inverse model. Okay, so then you can use like a 40 watts, okay, like 3D watts. You can see if I had an observation here. I had a phytoplankton, I had a zooplankton, I had for example, phytoplankton, right? I had a measurement. So then I want to do the inverse model. I want to see what kind of position, the uptaking rate, right? Mortality rate I choose. I can get some structure like observation. So this way you can tune, you can use the inverse model, data simulation inverse model, then you can determine what the parameterization is. So you can use data assimilation, the biological, determine the biological parameters. But don't simulation directly, like all variable. Okay? But I told you, sometimes not working for the data, parameterization. One paper they published, a lot of people cite, they do the couple part modeling in the Georgia Bank. They hear the observation couple part, he had a flu trying to put the couple part initial, he know the initial measurement, okay? Initial measurement couple part, then he had the next time you measure again, they're moving, right? So then he said, I put the initial condition, exact observation couple part in the water. So then assimilation, I didn't get, I run for example, the data, I didn't get, I compared the data for a couple of days later, I get nothing match, right? So then what happened, he said, okay, if you want to get this correctly for a couple of days later, I will determine what the position I should do. Like 3D or 40 watts, okay, determine the position. After this one, he said, that's the position. If I use this kind of grazing rate, mortality rate, I can get a match for observation. He said that really should be correct. However, after some people doing that, he found that the mortality rate he used is the most nonsense. Okay, for example, mortality rate, the observation show mortality rate for certain, for example, for some number, but he got a number 100 times larger. But people is published. Coding also available. Okay, but a good thing is people let them publish it, just let people know that's the method you can do. But then I was talking to them. I said the reason he did not good correct pronunciation because his hydrodynamics model not correctly. Because this 3D structure, he's a 2D model. That's why you get a transport everything done correctly, right? That's really, you probably have to, reason not to get a match, probably physical reason, but you climb is all inverse model climb, all is a biological reason, right? That's what you overestimate. But if you had a good physical model, you should use the inverse model to determine the polarization, right? You can do that, okay? Yeah, inverse, I can show you how to do that. I can reference the paper to you how to do that. So also you can get a coding. I'm pretty sure I can get a coding for you if you want to do that.
Yeah.
Okay.
Oh, thank you so much. It looks
Right.
really interesting. Yeah. Yeah.
Okay.
Thank you.
Next one.
Yeah, that's a very good question. No, I think the first thing is, yeah, if you output data, most time we output data is hourly data for offline. The reason because the file is so big. For hydrodynamics reason we put outline. For coast region, what reason we output data for offline is hourly because we find independent scale for flow is hour. Okay, if you reveal a current measurement, you go to current measurement, you do the call a time scale analysis, independent time scale analysis. Most coast region current separation time scale is hour. So that means inside 1 hour, velocity was related. Now after 1 hour, you get independent, right? That means you had to sample at least 1 hour. In the 1 hour, probably the linear changes something. However, that's not resolved. That's all analysis based on like a, generally like a tide circulation for other things, but not resolved like a mesoscale, like a front structure variability. Okay, but however, what it means is meso variability dependent what kind of front you study. For example, you have a mesoscale front, like a tide mixing front. So that's offline coding should be audio output should be enough. You should able to resolve that, okay? Because most like a tide mixing front, like around the front region, a lot of is a geotraffic current. Get a balance, okay? But like a Georgia Bank, especially tide mixing front due to by nonlinear interaction, the convergent, divergent, vorticity. That's different way. That's caused by topography. But if you know the core topography, most like a geotraffic flow along there. That's why, you use the hourly output should be able to resolve that. Okay. However, if you want to start the mesoscale variability, right? Like a high frequency like wave, like a turbulence wave, like an internal wave, you definitely not resolve that. Okay, so that's why you had to run online, even online. Okay, so you have to be resolved. So you can because online, so you can resolve a small time scale. You can do that. That's the reason you have to use online. Okay, but if you really want to see a mesoscale AD something like a very high frequency oscillation affect the phytoplankton, you have to run online. Offline, but if you want offline, you can do for short time. You have to output more high resolution time resolution, not a 1 hour, right? For example, mesoscale screen depend on frequency, depend on the spectrum you do. If you find a mesoscale variability, energy most take about 10 minutes variability, for example, right? So that means you have to resolve the data as every 1 minute, right? If you want to resolve that, that's better run online, right? So when you do how determine you do the spectrum, energy spectrum for the mesoscale. So then you look at spectrum, you see what is the most energy you want to looking for. Where is the frequency they are? So then you have to determine at least four, divide the four in the period for this short period. You can resolve that. Okay, that's why you use offline. Our offline reason most of it we study like a tide variability, daily, variability, also seasonally. Most ecosystem model, they introduce season variability. That's why offline is enough. Okay. However, if you really want to see some kind of, message scale, you have to use online. Okay.
I
So answer your
see.
question.
Yeah, I got it. Yeah, thanks so much.
Mhm.
Next one.
You know, that's just a first question very interesting. That's why you said, overcome the numerical, numerical, okay, the deterioration and the mass conservation. Yeah, no, in the online case, you don't worry about that. Because online case, because when you do, biological model, for the conservation, so that's a volume always conservative because it's a free count to find the volume model they have. They're all conservative. You don't need to worry about that. But then offline, you do have a problem, right? The offline, because you output data every hour, for example, you cannot run the model for every hour. You have to run for because 20 minutes, also second, 2 minutes or something. You have to make smaller. Then you do interpolation. You have to interpolation your fare between the, between the hour, interpolate to small time step. After interpolation, water conservation is broken down. You're not able to guarantee the water conservation. Okay, but after interpolation, right, you do the continuous equation, you can see they're not conservative. This way, what do we do? So we have an offline coding. We have four things we have to do called a volume adjustment. Volume adjustment what it mean? That means we do the interpolation data for time step you want to use. So then we recalculate the continuous equation. So after the recalculate condition, we adjust your omega vertical velocity, adjust the sea level, the total depth adjustment. So this means in that adjustment is each volume is conservative. You add together equal to 0. Right? You put a constant nutrient in, constant there, they not cause any variability, not cause anything. You guarantee that. After this adjustment, then you put a nutrient in there, you don't have a transport issue anymore. But then the question come up, sometimes your model had a big converging, diverging, sometimes depth change a lot. So now we make sure we get a very conservative way. We only do each hour, we assume each hour velocity, everything, no change in the 1 hour. Even we interpolation for many, many small time steps, we only determine the, next time step, the total depth. We put a total depth there, we change it, all hour is constant, then another hour is constant. This way, we can make sure the water conservation. Okay? So that's the way you can do. We pay a lot of attention, but some people like your people, they don't care. They just interpretation data for each small time. They do the ecosystem model, but they find it's also working. But sometimes depending on what location you are, right? If the estuary for shallow region, but deep ocean you probably okay because deep ocean time step velocity change is very slow. So that's why you can do this one no problem. But in the estuary, you got velocity change significant time by time, right? It's very significant. That's why you have to do the volume adjustment before you turn on the ecosystem model. Okay. The second question, I don't know. As a second question, yeah, you said phytoplankton was likely to be carried by the ocean current, then the swinging and on. No, it's how does it stronger, mechanical energy, the energy result for physical internal force effect stay available. Yeah, you do have, right? Because you look about ecosystem model, so you had advection inside the model, you had a vertical diffusion. All of the biological variable is it can be advected, also be mixed vertically, right? Also vertical advected, right? So so then you have a physical mixing, the variable also mix it. Okay, so that's why if the coastal water, if water mixing, for example, nutrient, you get a physical model, you determine what the nutrient, what the mixing coefficient is, then the nutrient was mix it. Okay, so if water stratified, then the thermocline, then the nutrient climb can develop. Everything look like a temperature if you don't consider lifetime, right? All the physical driving forces included in the model. Okay, so right, so that's the physical driving the timing of ecosystem bloom. That should be very interesting. Okay, most time the physical drive is the temperature. Okay, the bloom happen depend on if you're warming. The bloom happen if you look at the phytoplankton bloom, they control by the growing rate. Growing rate dependent on how much nutrient available, right? How much the more temperature condition you have the temperature. That's why the nutrient, where the bloom happen dependent on the growing rate. But growing rate is a function of a nutrient, functions of a temperature. Right? For example, you run a model, most time in the winter time, nutrient was mixing all the water column in the winter time. That's why surface nutrient high. Right? But in springtime, when the light enough, temperature is good condition, they can start to bloom very quickly. But after bloom happen, so nutrient will take over, then the nutrient with the surface most go to zero. Right? But deep ocean still have, but the phytoplankton grow up. You see what I mean? But then the phytoplankton was one phytoplankton spend most of the lifetimes of 14 days, 2 weeks. And after they die, so they will be sinking in the bottom, become dehydrated, then the detritus will come back the nutrient. That's the whole thing, not only physical driving. Okay? That's why how the ecosystem bloom happen really depend on the many reasons. Okay? How much nutrient you have, enough nutrient, also temperatures that is good or not, right? Because you got a certain favorable temperature, it can grow fast. Also depend on the light, because the primary production, right? Because the primary production, the light, you have the available light, the good light, they can, but it's not only physical driving, have a biological driving too. That's why, how to control that depend on the condition is. It's not as simple to tell you. If you can simply how to physical driving, you don't need to run an ecosystem model anymore. Right? You just put the physical force, you can determine like AI. Okay. 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 How about I address your question? Good.
Okay. So this is the last question. So is there any other question?
Actually, I have one is a different question, but as you said, the volume adjustment is like a tuning the vertical velocity to satisfy the conservation, right?
No, tuning the sea level.
Tuning the sea level, okay,
Sea level.
to
So
satisfy
when
the
you tune the
volume.
sea level, water velocity also be tuned.
Yeah, yeah,
So that's same thing, right?
right, right, right.
Because that's the sea level is not a true sea level.
Okay,
They just
okay,
want to make sure the water conservation.
yeah. My question is, how about the static effect?
Sorry?
Static effect, the expansion due to the thermal effect, the static, the whether the volume is expand when the if its temperature is high
Yeah.
or shrink down if temperature is not that strong. I mean that effect is called the static,
No,
right?
they only adjust the volume. They
Yeah.
don't.
So I mean,
Yeah, they don't only adjust the volume, but it's temperature variable. They look like a tracer turn. That's why they don't change the turn, because this all adjustment just want to get the volume conservation, just like a water flux equal net flux equal to zero,
mm-hmm,
right? So if you had a closing system like a box,
mm-hmm,
right? if you want to make sure your box, you can look about how temperature changes, for example, in the box,
Mm-hmm.
right? You have an inflow temperature, you get outflow water. So then if you want to see temperature change, you make sure your volume should be keep like a net flux be zero.
Yeah. My question is different. My
Okay.
question is, let's suppose there's a box,
Yeah,
and let's suppose there's water.
yeah,
If the temperature is higher, then
yeah.
volume have to increase.
Oh, that's not effective. No.
So that is called static.
No, that's the, but that's nothing related to ecosystem model. That's a physical model.
Yeah. I'm not talking about ecosystem.
Yeah. No, no, yeah,
I'm asking you totally different thing.
yeah. So yeah.
Yeah.
But,
So for the static effect, does that FVCOM combine the static effect in the model?
yeah, study effect. Yeah, you do. Because you had a you get a when the temperature warming,
Mm-hmm.
right? Temperature warming. So then the problem now you see what happened. We assume is a incomplex equation,
Mm-hmm.
right? That means
Mm-hmm.
no, everything's volume changes. Because if you had for example, temperature warming, the water can be expanded. It's
Mm-hmm.
not considered that because
Yeah.
you assume as an incomplex equation.
Yes. But some model, I heard that some model
Now
somehow kind
hydrothermal,
of
you consider that.
yeah, but all other I remember I heard that moms they
Yeah,
kind of include that kind of
yeah,
effect
yeah,
as a uh, I don't know how to do it, but
yeah.
somehow they tune.
But we can look Lamont. I don't think that I still think a coast region important part of climate change amount very important probably. The climate change
Well,
amount. But you
I'm
want
asking
to
this.
yeah,
Uh,
I don't
I'm
think we consider yeah. Yeah.
I see. I'm asking this question because sometimes in our region, the Incheon region,
Mm,
the M2 tide, the tidal components is that there's a definite seasonal variation,
mm-hmm,
and there's no other explanation but the thermal effect
mm-hmm.
can
Yeah,
be can be explained. That's
yeah.
why I'm asking this question.
Yeah, that's what if you look about if you wanted to do that, right? So you had
Mm,
a lot of when we do the before, so you had to have a diverging, converging should be equal to the density changes.
mm,
That's why you had to have you cannot use the incomplex equation.
mm-hmm,
I'm pretty sure Mang was using incomplex equation too. However, he
mm-hmm.
probably put assumption, some kind of
Yes,
assumption there. But if you
right.
base it on a really about the equation, you have to do because you not be incomplex anymore. You get water can be dependent temperature, convert the water can be changes, right? Can
Mm-hmm,
expansion, shrinking. But this way
right.
you have to have a d log dt equal to
Mm,
converging diverging. You have
yes,
to
right,
have a d log dt equal to log times converging diverging. But now
right.
we assume this is everything equal to zero. That's why d log
Yeah,
dt not there anymore.
right.
So then, however, like some GFT coding, so we
Mm-hmm,
do consider that. So that's why sometimes I ask, Glenn Floor people, we always MIT professor, we also argue each other about this way. I said you assume the converging diverging, then you assume no d log dt can equal to something.
mm,
Okay,
mm,
it changes, but this is linearly.
mm,
Okay,
mm.
they had a linear equation. The log dt had a converging, diverging change, but take a nonlinear out.
Yes, I see.
See, I'm pretty sure Mount you do this way. So this way,
Mm,
the volume can be changes, but certain range this one. But then how but this condition is a controversially with a complex equation.
mm,
But
mm,
this law that's working,
mm.
right? My
I
my
see.
GFT course with some people did this way, but.
Okay.
That's some people, I think that this is very critical. It's a very interesting question. But a
Mm,
lot of people do the climate change model, you have to consider that.
mm.
Right? You have to because of warming, right? Volume can be
Yes,
changes,
yes.
right? Very simple example. You have water in the cap. You heat the water, right? then you can see the water probably go a little bit go higher.
Yeah.
So that's the infection, yeah. Okay. But for this equation, we don't consider that, okay?
Okay.
If some student like to do, I can show you how to do that, okay?
Okay.
But non-hydrostatic model sometimes also not resolved because non-hydrostatic still shown as a convergent free, divergent convergent free. This way you said no, but you can add this term, okay? Just change the density equation.
Mm.
Okay. If you have no question, let me stop here.